Hi everyone. So today we'll be solving problem 3 on assignment D. So a long wire of circular cross section has a radius of A and is centered on the z-axis. Uh, so it has permeability mu naught inside the wire. The wire is coaxially surrounded by a hollow cylinder of material of uniform magnetic permeability mu is equals to 3 mu naught in the region 3a s. S is between 3a and 2a. Aside from this region, mu is equals to mu naught everywhere else. A current I naught is uniformly distributed within the wire. That is basically the current density is I naught divided by pi a square z cap. So the current is in the z direction when s is less than a. So what is h for s less than a? S is between a and 2a, and when s is between 2a and 3a. Okay, so we can find this basically simply by using the Ampere's law. But before even I start that, I've taken the liberty to draw the diagram here. Okay, so this is the wire. Okay, this is the wire that we are talking about that carries current in the z direction. Okay, it's surrounded by so the wire. So as you can see, the wire is of radius a. Then from a to 2a, it's free space. The vacuum is surrounding it, so mu is equals to mu naught. And or we don't know if it's vacuum. It's basically surrounded by, is it vacuum or what? Yeah, it's we don't know if it's vacuum, but we know that the magnetic permeability here. So let's say this is region 1, this is region 2, and this is region 3. So region 1 and region 2, and again this is region 4. Region 1, 2 and 4 have magnetic permeability mu is equals to mu naught, but region 3 has magnetic permeability mu is equals to 3 mu naught. Okay, so now to find out the magnetic field intensity, we know the Ampere's law. Ampere's law states that integral of h dot dl over a closed surface is equals to the enclosed current. Okay, so we can pretty much find what it is. Now because the current has a circular symmetry and it is flowing in the z direction, we can refer to h as the azimuthal symmetry. So h becomes h phi of s integral of dl is equals to I enclosed. So basically, if you draw an imaginary Amperean loop, the loop could be of any dimensions. For now, I will draw a loop which is basically in this region. So let's draw this loop in this region. So let's basically draw the Amperean loop. So the Ampere loop, let's say its radius is when measured from the center is s. So then the integral here becomes h phi of s 2 pi s, because the Amperean loop has a circumference of 2 pi s. That's the closed path integral. That's equals to I enclosed. So now this is the equation that comes out of it. Now let's see what happens when there are three conditions, right? When s is less than a. So h phi of s 2 pi s is equals to I enclosed. For s less than a, when s is less than a, I enclosed is going to be depending on, so I enclosed is in the region 1. Okay, we are talking about region 1. So in region 1, I enclosed depends directly on the value of s. So we know that j is dA. Okay, I enclosed is equals to j dot, this is the area, current density dot product with the surface area. So so then basically that means current density area is basically the we're talking about this area. Okay, so area then becomes s ds d theta. Okay, that's the area is z cap. It has a direction z cap because it's the outward normal. So based on 0 to s, okay, you could write this as s dash d dash 0 to s. So the current is directly dependent on whatever the value of s is. Okay, so this formula then gives you h phi of s is equals to I enclosed by 2 pi s. So find out what this value is. We have done this thousands of times over the course of this semester. This integration is very simple and straightforward. Substitute the value of j that is given to us. J is said to be equal to, we know that j is equals to I naught by pi a square, I naught by pi a square z cap. Okay, so this is, substitute that formula there and find the value of h phi of s for s less than a. Now when s is greater than a, so when s is greater than a, so the next region is when basically that implies when s is between a and 2a. So this is the second region, and then in the third region when s is between 2a and 3a. Okay, so the thing is, in both of these cases h of s is again going to be equal to I enclosed by 2 pi s. But now remember that the I enclosed does not change in either of these cases, because current was only flowing until s was equal to a. Anything beyond a, there is no additional current flowing. So I enclosed is going to be the same I naught that's given. So h phi of s then pretty much is just this is equal is this. So so for s greater than a, it'll be just this one, and for s less than a, you'll have to find out this I enclosed. Okay, an integral. This is the only part of the job that you have to do. Thank you.